Hi everybody, Miss Wombold here. Sorry I can't make it to class, but what I've left behind is a skills review. This is a good point in the unit where even though we've learned a lot of stuff and it's all related, I think we should just stop and make sure that we've got all the pieces together and we're all caught up. So as you watch this video, there's lots of parts to this packet. So between each one, I'm going to ask you to pause the video and complete the remaining exercises for each part. And then you can come back to the video and we'll start the next examples together. So, part 1, domain and range. Remember that domain refers to the x values covered by the graph, range refers to the y values covered by the graph. So on our first example A, the first thing I should notice here is I've got an open circle on the left side and a closed circle on the right hand side. The open circle, you remember, means that that point has been taken out. So even though we see a circle there, the graph doesn't actually cover that point. Not like the closed circle here where it means the point's been filled in, poop, fill it there. So, domain, x-axis, left to right. So I start with the very leftmost side of the graph, and I can see that it goes all the way to this value, -5, and it covers everything from -5 all the way to +5. So when I write my domain, I'm going to make sure that I have -5 on the left-hand side, x in the middle, and 5 on the right-hand side. And then here's the part where the open and closed circle comes in. The open circle means I don't include the equal sign. I do not put the equal sign there because it's not quite equal to that point. Not like on the right-hand side where I've got to put the equal sign because it's all filled in. Now when we write from smallest to largest, left to right, our inequalities are always going to open the same direction. We don't have to worry about that at all. Our range, on the other hand, y values, so we start from the bottom to the top because our smallest values are at the bottom of the graph, the largest values are at the top. So the smallest values, the graph does not go below the value -2, and it doesn't go above the y value 2, but it does cover everything in between. So when I talk about the range, I'm going to have -2, my smallest value on the left, y in the middle, +2 on the right because it's my largest value. Now, even though I've got an open circle on one of them, the fact that I have this line segment and a closed circle over here, it means that the graph does in fact have a value at -2. It just doesn't have one here, but it has one over here. So we are going to include an equal sign on both sides of y because both -2 and 2 are included in the graph. So examples A is nice because we've got the graph completely enclosed left to right, bottom to top, and we can state the values here, and that's all we have to do for the domain and the range. Example B, key difference here that we should notice on the graph is that there are now arrows at the end of the graph, which, as you know, means that the graph extends forever. If we think about what happens when we zoom out, we would see, of course, the values change on the axis, right, get bigger and bigger, but the graph would also continue to the left, continue to the right. So when we think about the domain in this example, it's not just what we see here. It's not just -5 and 4. It's not just -6 and 6, right? This graph would continue to extend well beyond what we see. And we know that the further left we go, the closer we get to -infinity, the further right we go, the closer we get to +infinity. So there are two ways that we could write our domain here. We could write as x from -infinity to +infinity. The other way we can write that is because it includes every single number in between, the positive numbers, the negative numbers, the whole numbers, the decimals, everything. We can also write it as all real numbers. Those are exactly the same thing. They mean exactly the same thing. We don't have to write it both ways each time, but we should just recognize that it's the same exact thing. Now the range, on the other hand, yes, we still have arrows. It's the same graph, but notice that the arrows are only pointing upwards. There is a limitation at the bottom of the graph. It never goes below this value, y equals -3. It does go up above it, and it will continue to do that forever and ever and ever. So when I write my range, I want to make sure, okay, we stop at -3 on the left-hand side of our inequalities, but we can go all the way up to infinity. So it'll go up and up and up forever, but never go below -3. So we just can't include negative infinity here because it never goes below -3. At this point, I'd like you to pause the video, complete numbers 1 through 4 on this page, and then I'll meet you back on the next page for part 2. All right, ladies and gentlemen, I hope part 1 went well. Remember, if you have time before the end of class, you could always go back and check your answers with your neighbor if you felt like you needed to. Part 2, function or not a function. So here we're making sure that we understand how to identify whether a mathematical relation is a function or not a function. The key feature to a function is that each x value or input has one output. It could be the same output for every single input. That's okay. It matters about the input. Which x value am I using? Different x values can all have the same output. That's okay. But if I have one x value with two outputs, that's where the problem is. So if we're working with a set of ordered pairs, remember it always goes x and then y in alphabetical order. So if I check my x values here, I've got 1, 2, 1, 4, 3. Now the fact that I have two 1s here, okay, that's a little bit of a red flag. I should probably check that out. And as it turns out, each one of those points has a different y value. So right away, we can say this is not a function. That's all I have to do here. I can do the same thing with the table. So I check my x values, -2, -1, 0, 1. Okay, I don't have any repeating x values, which means, okay, -2 has one y value, -1 has one y value, 0 has one y value, 1 has one y value. Nobody in the x column has more than one y value, so we are good to go. This must be a function. Last but not least, when we have a graph, we have a shorthand here called the vertical line test. Remember that every point that's on the same vertical line has the same x value. So if I draw a vertical line here through this point, every point that appears on it has the same x value. There's only one point here. But over here, this is the line x equals 3. And as it turns out, we've got 2 points on it, 3, 3, and 3, 0. So the vertical line test is a shortcut to make sure, I've got one x value, 3, with two different y values. So that's a problem. That is not a function. It doesn't matter what the graph looks like, if it has arrows at the end of it, if it doesn't, if it's discrete, if it's continuous. All that matters, one x value, one y value. So pause the video here, complete the rest of part 2, and I'll meet you back on the next page for part 3. All right, welcome back to part 3. This time we're talking about function notation and graphs. So one quick reminder about function notation. Anytime we see f of x or any other type of letter, that's just a name for a function. It's the same thing as a y value. And anytime we see a number inside parentheses, we can always remember that is an x value. Anything outside of it set equal to this is a y value. So in our example graph, we've got two lines on the same set of axes. We've got f of x and we've got g of x. So two names for two graphs. So when we look at the questions being asked of us, it's important that we note first, what are we being asked to find, and then how are we being asked to find it. So f of 5, this 5 is inside the parentheses, so it must be an x value, and it's got f in front of it, which means we're referring to the line f. We can just ignore g for a moment. So I find the x value 5. Here's the x value 5. And I'm going to go vertically upwards until I hit the graph. I intersect it right here, and when I carefully check the y value of that point, it turns out to be 5, 8. So when my x value is 5, my y value is 8. Part B asks for something similar. This time it's g of negative 2. So I'm using my graph g, and this time my x value is negative 2. So on my x-axis, right, horizontal axis is x, I find negative 2 right here. Now I'm going to ignore f of x, right, that's not the line we're talking about, but I'm going to go all the way up to g of x. Whoops, went a little bit farther. There it is. So when I carefully check out where that is, that appears to be the y value 3, point negative 2, 3. So I can say that g of negative 2 is 3. Now question C is a little bit different here. This 6 is outside of the parentheses, so it's, oops, sorry folks, not an x value. This says f of x equals 6, or the y value of f is equal to 6. So now I'm talking about the y-axis. So this is where I start, is on the y-axis. I find 6, and I'm going to go until I hit the graph f of x, right, ignoring g of x for right now. And when I figure out what x value that is, it turns out to be 3. So when f of x equals 6, x equals 3. Likewise, part D, if g of x equals 6, okay, so now we're going to take this all the way over to g. Looks like it's just past the x value 4, maybe 4.25. It's okay to estimate it. We are working with a graph here. We're not working with an equation or an exact value like that. Part E, which has a greater value, f of negative 4 or g of negative 4. So both of them are talking about the same x value, negative 4, but we're comparing the y values here. So this is why it's important that we have function notation, because we're talking about the same x values, we're talking about y values, but they're different numbers, so we can't just call them both y values. That's why we have f and g. So to answer this question, I'm going to find x is negative 4 right here. There's negative 4. So I can see exactly where each point is. I can either identify the values. I can say that f of negative 4 is equal to negative 1, and g of negative 4 is equal to 2. And I can say, okay, 2 is greater than negative 1, so g of negative 4 is greater. So no tricks there, just trying to figure out which has the larger number, the larger value there. Finally, on what interval is f of x greater than 2? So this is asking if my y values for f, I can see the y values, they're aligned, they go across the graph, where are they bigger than 2? So the first step is to figure out where is y equal to 2. And everything above this line is where my y values are greater than 2. So for f of x, my yellow line here, I know it's getting a little bit messy, my yellow line, the first time that happens is right here. And everything to the right of that, it's always bigger than negative 2. Everything to the right of this little point is always bigger than negative 2. So when I talk about on what interval it's happening, well, I know that the y values are already bigger than negative 2. I'm not going to talk about those. What I am talking about is I'm going to say that when x is greater than negative 1, or another way of saying that is negative 1 is less than x, which is less than infinity. So every x value between negative 1 and infinity is where the function is greater than 2. Take a couple minutes to process this. See if you can answer the rest of answer the questions about the remaining 2 graphs. And when we come back, we're going to be on part 4. Alright, welcome back ladies and gentlemen to part 4. This time we are interpreting function notation. So instead of just identifying what's our inputs and what's our outputs, we're actually attaching meaning to it, which is probably the hardest part of what we've done today. So we're going to take our time with this example, and then you're going to do the scenario number 2 on your own. This will be the last part that we go over together on the remaining part of this packet. You can use your notes, you can use the cheat sheet that's on Canvas in Module 3, you can refer to your neighbors, but the rest of this packet you are going to do on your own. So let's get started with this example. Lisa collected data on the number of feet she could walk each second and wrote the following rule to model her distance in feet over time. So her rule, d of t equals 4t. That shadow you saw was my cat. D of t equals 4. So this means that the distance she can walk related to the time. So t is time. T is time. And d of t is the distance per that time. So the distance at that time. Which makes sense. So if we say, what is Lisa looking for when she writes d of 12 equals blank? We notice that there's a number inside the parentheses, which was the time in our original function, and it's inside this function d of t. So what she's looking for, she is looking for the distance at 12 seconds. Now, notice there's nothing more to this question. We don't actually have to figure out what it is. Although we could, what we are doing is we're trying to interpret this. We're going from the algebra and translating it to English. Let's practice again with part B. In this situation, how do we interpret d of t equals 100? So this time, the number is outside of the function notation. We have no number inside the middle. We're not given a time, what we're given is a distance. So all this says is the distance is 100 feet. This question doesn't ask us to figure out what the time was, although we could. We don't need to do that at this moment. All we have to do, again, is translate from the algebra, d of t equals 100, to the words that distance is 100 feet. Finally, what does this phrase d of 5 equal 20 mean in the context of the problem? Well, we know that 5 inside the parentheses is the number of seconds, and we know that 20 set equal to d is the number of feet. So when we break it down into those two parts, identify the components, we can put it all together again into one sentence that says the distance at see what I did there? At 5 seconds is 20 feet. So take your time with these. Really interpret, where is the value that you're given? Is it inside the parentheses? Is it outside the parentheses? And make sure you understand, make sure you have an idea of which variable represents what value. If it depends on time, that's why we have time inside. The distance depends on the time. So go ahead and finish the rest of this packet. It's due at the start of class tomorrow. Do your best, talk to your neighbors, use your notes, and I will see you tomorrow. Good work today, guys.